Right. So we are on the middle of this process of routing this memory with this system on a chip. So in some posts I call this a CPU, but as this is a system on a chip is more than a CPU, is a CPU plus a GPU and so many other structures. And talking about routing, uh, first of all, when we are discussing about routing um, printed circuit boards, we first need to determine things like the stack up of this board, and as we are dealing with a computer, so this is a computer. We are routing a system on a chip with a DDR LPDDR5 memory and also a flash memory. So basically, we are putting together parts uh, to to construct a computer. And okay, as we are routing a DDR LPDDR5 memory um, to a into a into the system on the chip, which is the RK3575, and sorry, is the RK3576. So we need to first determine the stack up, because um, let me show to you the schematic. So um, I'm doing a reverse engineering into a piece, and so this is the piece that I'm reversing. So I'm basically first I put the part together. So first of all, shout out to EasyEDA to be one of these CAD design tools that it makes available uh, a great number of parts. So because of this, I'm capable. I'm able to put this board, these parts together to construct this computer. Um, so I can show you the 3D view. Okay, this is the 3D view, and this is the board that I'm trying to replicate. And to replicate this board, um, the easiest way is to first put the parts together. So again, EasyADA is one of these CAD tools to draw printed circuit boards that has the available the a great um, number of components. So if you look at the library, you for sure will find what you need. And laying out the parts, laying out the parts is easy because we are basically just replicating this piece, and now we need to route all these traces, and now we need to look up for all the schematic parts. And Of course, we need to read these schematics, these documents, and right here I have the system on the chip, the RK3576, and when we are working with memories, um, when we are routing memories, um, things that we're going to find is group of signals. Um, so when we are routing a memory, we will have a data group of signal. We will have strobe group of signal. We will have mask and addresses and banks controller signal. We will have clock signal, and this group of signals we will route in in layers. So each group of signal will have a separated layer where we will route them. So as you can see, we are defining a stack up of 10 layers. So on the first layer, we can route high-speed signals, and on the second layer, we have a reference plane to these signals. So we have a ground plane as reference, and on the third layer, we got another group of high-speed signals. On the fourth layer, we are uh, defining a power plane. Um, the fifth layer, we are routing more high-speed signals, and on the layer of number 6, another ground plane, which is again a reference plane for the signals. On the layer of number 7, high-speed signals. On the layer 8, a power plane. On the layer 9, another reference plane, which is a ground plane, and again on the layer 10, more signals. Okay, so we are defining to the layer 1 the group of signals DQ. So is 32. So DQ0, it goes to DQ7, which is the byte 0. So we got 4 bytes divided by into these DQ signals. Each byte it got 8 bits, and still on the layer 1 we will write the group DQS. On the layer 3 we will route the data mask. On layer number 5 we will route the addresses, and on the layer still under layer 5 we will route the banks, the signal of the banks. Still on the layer 5 we will route these signals of controller. These are controller signals. Under layer 1 we route the clock signals. And right here on EasyEDA, something that we unfortunately cannot do is divide this group of signals into a group so we can route them together. But to help us, what we can do to help us on this process of routing, we can change the net color. and change the net color, we can identify more easily uh, these BGAs, the pinouts, and this is make easy the process of routing. So for example, if we wanted to identify the GND, we can come here and clicking with the right button of the mouse and come here in net color, and we can change this for blue. So as you can see, we changed all these BGAs to the blue color. So okay, this is we will be into a polygon region, and actually we won't route a signal into this BGA GND pads. Uh, but for example, uh, if I come here on schematic, and we got another sheet for this schematic. So right here we got the PMM, which is the power managed module. We got our flash memory, and we got our RAM, which is the LPDDR5 technology, and our EEPROM also. Right here, we are assigning these net labels to these pins. So right here is the group DQS. So if I click on this pin, I can identify the pinout right here. I can identify this BGA, and I can change its net color for, so I can identify when I'm routing. Right here, net color, and let's change for orange. Okay, and this also a DQS signal, net color orange. In this way I can identify this group of signals. And now for example, as I'm doing a reverse engineer on this piece, uh, I I need to assign um, each of these pins a net label. So for example, I know that I'm dealing with all the signals, and this is something that I took from its schematic, the schematic of the the RAM. So right here I got the RAM, the LPDDR5 datasheet. So all these PGAs that we are seeing uh, on the datasheet, they have a different color, so we can identify, for example, all the DQ signals, they are with this color green. The VDD signals, they are with the red color, and VSS, which is the ground, they got this blue color. And the same we can apply right here. And this part is the system in the chip, and this part is the LPDDR5, is the RAM memory. And okay, I'm doing this reverse engineering, and for example, I'm routing first this group of signals, DQ, DQS, DQ. Right here we got DQS and DQ. So let's say I wanted to identify this DQ group right here on the RAM. So right here is easy. I can identify right here DQ. So let's see if it got the same net. So DQ11A. What else we got? DQ11B. So let's do a count. These are 1, 2, 3, 4 bytes. So it's 8, 32, 40, 48 bits, 56 bits. Oh, sorry, 32 bits. 8, 16, 24, 32. 32 bits. So 32 signals to route. And we can also see the signals on other structures, other block diagrams on its datasheet. So we can route two parallel LPDDR5, but right here we are only working with one. And right here on the description, you can find a bit more, you can learn a bit more about each of the signals. So as you can see, we got the clock signal, which provides to us a base time to work with synchronous systems. We got the chip select, CS, we got this command address, we got the DQ signals, and DQS, the masks. Let me change the signal DQ for this appropriate color, green. So this is the QS. It got this color, green color. So click on the right button of the mouse and come here on net color and select the color. And again, this is will make easy the process of routing. And now we just need to identify the same net right here on the RAM. So right here on the RAM, DQS. And okay, so DQS. As you can see right here on the net, we got P and N. And I'm guessing this is positive and negative. So this is probably for we will have to do a differential routing. These are differential signals. So we can check this on the schematic. So open the schematic right here, DQS, read data strobe. So these are differential output clock signals. Okay, so this is our differential signals exactly. So this is why we got a P and this N, so positive and negative, so they are differential, and they are used to strobe during use it on the data during a read operation. Also use it as a parity pin during write link protection enable. Okay. Okay, so now confused about the number of signals. So for example, we wanted to route this system on a chip um, with this RAM memory, this LPDDR5. And on the RPDDR5, we can count, let's see, 1, 2, 3, 4, 5, 6, 7, 8 DQS signals. So, and let's check these 8 signals, its correspondence on the system on a chip. So what we can do, if you press Ctrl plus F on your keyboard, it will pop up this window, and right here we can search for the signal. So type DQS and press enter. Okay, so let's see the number of signals that it returned to us. DQS. So right here, 1, 2, 3, 4, 5, 6, 7, 8. But also, I think he's counting the number of the other shit as well. 9, 10, 11, 12. 12 signals. But, okay, so it's identified only on this sheet. Okay, and these are some DQ right here too. DQS, we are looking for DQS. DQS1, okay, that is correct. We are looking for DQS0 and DQS1, DQS1, DQS1B. So let's try this net, this pin, DQS1. DQS1, and okay, DQS1. B. Let's say this one, and also a positive, a negative. Okay, and save. This is A and B. Okay, and now We can come here on design and import chains from schematic, apply chains, and automatically already change the net color. As you see, and this is DQS1 positive B. Let's see this one. This one, both are B. Okay, so DQS1 positive B again, negative B, or we are looking for a positive DQS1B. This is B and this is A. One needs to be the positive and the other it needs to be the negative because these are differential signals. Okay, now save. And on the upper menu, design, import chains, apply chains, and again already changed the color automatically. And now we are ready to do this routing. So let's try. So we can come here on, just select this signal routing, and even the color of the net already is green. And right here in property we can change, so let's see the width of the net that we are using. So we are using 5 mils. So again, so let's change for 5 mils. And now we can do this routing. And remember that I said that when routing we need to pay attention to not blocking out the path of the traces. So this is why we need to do the order that we follow to do this routing. We need to do first the outsiders and on the last the insiders. So this balling is outsider in relation to this baller, and this baller is insider in relation to this balling. Sorry, this balling. Okay, so we need to erase this routing and do this first. And okay, right here we will need to create a individual rule, and as we are routing these differential signals, its length we need to match. We need to left the length of the signals. So again, I block out the path of this trace. And even that this bowling is outsider in relation to this bowling, but let's try. We can come here, outsider of the bowlings, so we don't block out the path for other traces. We are using 5 mils. I will erase this as well. And now this one, change to 5 mils. Okay, we can do this way. And I'm committing this mistake. These nets, they are with the same net. So let me correct this. I wanted to find is differential pair. DQS1PB. DQS1. Right here, let's see this. E, this B. Now I save and import chains, apply chains. Alright, and it's right here, very away from it. Let's see this way. This is BA. B, A, this is positive, negative, or let's see if this is positive, and both right here, they are negative. Let's see. Okay, now it makes sense. And the signals now they are correct. Alright, so probably this is the correct way. And now let's try with differential routing. So right here on routing, and we can use, let's see if we have differential routing. Differential pair routing. So differential pair 1, and this is okay, DQS 1 and B, and DQS, so type DQS 1 and a positive and a negative signal. Apply and confirm. Sorry, routing, differential pair routing. I commit a mistake right here. Let's do it again. Routing, differential pair. I select two negative. It needs to be one positive and the other negative. So again, routing, differential pair routing, and click on the polling that we wanted to route, confirm, differential pair 1, and DQS1 in negative, B in DQS1 positive, but it's only identifying the nets with A, and none of this is B. DQS1 and both are, or just A. Let me see. Right here is B. Okay, if I try to route this differential pair, as you can see, its other is opposed signal is differential, is very away from it, and it will try to trace the path. We will try to trace this path, and is a path that um, we as designers we already can see that it's not a good path. It's doing too much loops, and even let me change the length again. if we try to, yeah, with this automatic differential routing, it's not working very well. And also, right here, I'm just changed the net, but I will see exactly if this is correct. They are corresponding very well. But when we are trying to do a differential routing, this net is doing pair with a net very away from it, and now it's not making sense. But this is something that we will see on the incoming videos. And for now, this is all that I wanted to discuss with you on this project that we are doing. So uh, first, we will route a group of signals. So we are working with DQS and DQ signals. So the DQS group of signals, we will route on the first layer. Also the DQ group of signal. So something that I recommend to you is come here on the symbols, and you can look on the description of the pin. As you can see, DQS positive, DQS negative, and you place a net label and type these names. So place all the net labels, and after this you need to identify its correspondence also on the RAM memory, on the LPDDR5, which is the technology that we are using, and save and apply the saves right here on the design. And after, I recommend to you to change the color of the net, to change the color of the polling, so it's more easy to identify this. And when we route this bowling, uh, the trace already will assume the color that we change. Okay, so on the next video, I will see what is the correct differential pair, so we can do this differential routing again. Oh, now is correct, but this is not being identified as a differential pair, and I wanted to. So even if I come here, it's not identifying as a differential pair. But assuming that this is differential pair, what we need to do is to match the length of these traces. So for example, if we left above the trace the pointer, you can see these informations, the net length, the width of the net. So we are using a width of 5 mils, so this is for control, impedance control. And the net length, it has 350 mils, and the other, it has 412 mils. So we need to take this difference of this net and add on this net. So we are doing this manually, so we can come here on again routes and equal length tuning. And if I click right here, so I wanted to with a length of 4020 for 400, sorry, 420. 420. Okay, 420. So now they have 420, 421, the same length. So this is how we can do it as well. Okay, and for now that's all. Hope you like it, hope you enjoy it. And this is a study that I'm doing. I'm trying to put this board together, and let's see. Thank you.